Okay, in this video I'm continuing on with the discussion of blocking probabilities, and this is the third video. I just finished the second video where we have in summary a coverage of parallel links and series links, calculating the blocking probability of a bunch of links in parallel and a bunch of links in series. Okay, and these are the equations that we came up with. Now I'm going to talk about a situation where we have combinations of both series and parallel links. So combinations of series and parallel links. Okay, and I'll just do a couple of examples. Okay, let's take this configuration. Let's take the configuration of two series links where each link in the series is made up of two links in parallel. Okay, so we've gone from point A to point B in two hops in series, but each of those series hops is a parallel link. Okay, and let's assume for simplicity that all these probabilities, all these blocking probabilities are P. Okay, let's calculate the blocking probability of this entire link, P block from A to B. The first thing we're going to do is we're going to rewrite this diagram as two simple links in series, and we're going to calculate the new probability for each of these things. It turns out that when we have two links in parallel, the blocking probability is the product, or if they're both the same blocking probabilities, it's p raised to the nth power. So this first link has a blocking probability of p squared. The second link has a blocking probability of p squared. Okay, but now we've reduced this to a simpler problem where we have two links in series and we know each of their probabilities, and so now we can write P block from A to B is equal to, well, when I have two links in series, the blocking probability is 1 minus the product of the 1 minus the p's. And so here in this case we have 1 minus p1. p1 is p squared, and the product of 1 minus p1 and 1 minus p2. But p2 is p squared also. And so this is 1 minus the quantity, 1 minus p squared, quantity squared. So you can see the equation that we've derived in this simple case. Another example is just the opposite case, where we have two connections in parallel, but each of them is two connections in series. So I'm going to call all of these blocking probabilities P for simplicity of the example. And I'm going to write that this is equivalent to this diagram, where the blocking probability of the top branch, P1, is, let's see, it's 2 in series. And when I have series links, I have 1 minus P, the quantity 1 minus P raised to the nth. And n is 2 here because I've only got two links in series. And so P1 at the top is 1 minus P squared, quantity squared. P2 at the bottom is the same thing, 1 minus P squared. And so finally the blocking probability from A to B is, now let's see, I've got two links in parallel. When I've got parallel links, I just multiply their probabilities, and I have those two probabilities. So the blocking probability is P1, P2, right? And so this is And P1 and P2 are equal, so it's just P1 squared. And so it's 1 minus P quantity squared. Because that's the thing, and now it's that thing squared. Okay? And so those are two of the simplest examples we can come up with where we're combining series and parallel links. Okay? I'll leave it to you as an exercise to show that if all four of these probabilities are different, suppose we have something like the following. If we had P1, P2, P3, and P4 from A to B, then we're going to have P block from A to B is 1 minus P1, 1 minus P2, quantity, multiplied by 1 minus P3, 1 minus P4. Okay? And, oops, sorry. And similarly, if I go from A to B over parallel links with probabilities P1, P2, P3, P4, I'm going to PAB equal to 1 minus P1, P2 times 1 minus P3, P4. Okay. Yep, those are right. So those are a couple more quick examples. Next video I will talk about the three-stage clause switch.